Hello everyone, and welcome to today's chem lesson. Today we're going to talk about how we use balanced equations once we have them. Right? What's the point of balancing an equation? When we look at a balanced equation, like this one up here, we can infer a bunch of information about the molecules, moles, atoms in this equation. Seeing 2H2, O2, and 2H2O, we can look at those and conflate them to molecules, right? Say that that's 2 molecules of H2, 1 molecule of O2, 2 molecules of water. Or we can talk about them in terms of moles. 2 moles of H2, 1 mole of O2 makes 2 moles of water. We can also use what we know from the periodic table, right, these mass numbers, to go and say 2 moles of H2 is 4 grams of H2. 1 mole of O2 is 32 grams of O2, right? We can make them into their mass numbers. We could do the same thing, but with AMU for the molecules. And so we get a lot of information from a balanced equation. We are going to focus on the bottom piece here, the moles and grams, because those are the values that we can work with in the lab. You are very lucky if you have a lab that can work at the molecular level. Right? It is not a common thing. And so when we look at things, we are aiming to look at the moles and grams aspect of an equation and to work with that in a way that makes sense for us. A balanced equation is just like a recipe. When I want to bake cookies and I find my cookbook and I open it to the cookies page of the cookbook, there is a recipe there. And it reads out something plus something, bake at this temperature, blah, 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 you get some cookies. Let's say that recipe in the book gives me 12 cookies. Right? A dozen cookies. That's not bad. That's a pretty good number of cookies. But what if I'm baking cookies for a big party? What if I'm baking cookies for a birthday party and I need to feed 40 people? 12 cookies is not going to be enough. Does that mean I close my recipe book and put it away because it doesn't have the right number of cookies? No, it means I do a little bit of math and adjust. I take the recipe that gives me 12 cookies and maybe I multiply the whole thing by 4. That way I get 48 cookies. That's plenty of cookies. Maybe my recipe makes 12 cookies, but I'm just cooking for me, and I really only want a small batch of 6 cookies. And I cut the recipe in half. Right? You can do that manipulation. That is not a new skill. But we are going to take that exact thought process and we are going to apply it here to our balanced equations. We're going to treat them like recipes and see what we need to do to make the thing we want to make, to get the thing we want to get. And when we look at that, we're really looking at 3 different things. We're looking at converting moles of one thing to moles of another. We're looking at converting moles of one thing to a mass of a different thing. We're looking at converting mass of one thing to moles of a different thing. There is also the option of converting from mass of one thing to mass of a different thing, but that is more of an AP topic, and so we're not going to actually cover that today. We're going to start up top and work our way down from the easiest to the most difficult things to do. And our first are mole-to-mole calculations, converting from moles of one thing to moles of a different thing, is exactly what I was saying before about adjusting a recipe. It's taking that whole balanced equation and doubling it, tripling it, quadrupling it, dividing it by 2, right? Adjusting it so that it makes the thing you want to make. Let's take a look at what that looks like. Like I said, we're looking at a balanced... excuse me, hold on one second. Sorry about that. We are looking to mess with this equation. We are looking to take this equation and first balance it. H2 plus some O2 makes some H2O. We're looking to take this equation and adjust it to make what we want to make. But before we can do anything, we need to balance this equation. So let's do that. These happen to be the same equation that we were looking at before, so we're just going to do 2, 1, and 2 in order to balance it. This is the recipe from my recipe book. This is exactly as it is written. And now I come to that recipe and I say, I want 1 mole of oxygen. How many moles of H2O are going to go with that? And so my question now becomes, if this is a 1, what is this? And you'll see, I actually created little fractions by writing it out this way. Right, let's switch over to light blue here. I've got 2 little fractions that I made. And these little fractions make what's called a mole ratio. We can compare the moles from the balanced equation to the moles from our problem in purple underneath. My recipe is written in a way that says 1 mole of oxygen will give me 2 moles of water. So here I don't actually need to adjust my quote-unquote recipe. It's a 1 for oxygen, which means I'm going to have a 2 for my water. Using the mole ratio is the most important thing when you are doing these kinds of calculations. Anytime you are using a balanced equation, you are going to need to use a mole ratio at some point. Writing it out like this, putting your balanced equation together, and then putting what you want underneath it to make these little fractions will always be the easiest way to get it done. You're never going to confuse it and put the wrong thing on top or on bottom. Right? You're never going to have the wrong numerator or wrong denominator if you set it up this way. Now, what if my question didn't ask for 1 mole of oxygen? What if it asked for 4 moles of oxygen? What if this was a 4? Right, then I put my 4 underneath, right? 4 moles of O2, so put the 4. How many moles of water will be produced? Now, when you're solving this out, right, it's just like adjusting your recipe. This is what the book says, 2, 1, and 2, but you want to use up, or you want to make 4 O2s. So how many waters are required for that? I went from a 1 to a 4, so I multiplied this by 4, so I should multiply everything by 4, which means we're going to have 8 moles of water. That's the relationship here, so it must also be the relationship here. You could also, if that's not the way your brain works, you can also look at the relationship of the numerators and compare that to the relationship of the denominators. From 1 to 2, I multiplied by 2. I doubled to get here to here. And so here, from 4, if I multiply that by 2, because this must be the same, I'm going to get 8 again. Right? Whichever way you like to look at the relationship, right? Either numerator to numerator, denominator to denominator, or numerator to denominator, numerator to denominator. Whichever way you like to look at that relationship, you still get 8. Notice that H2 doesn't come into play at all here, right? We never even went over here to look at this. H2 is not involved after we just balance the equation. Once the equation is balanced, this isn't part of the problem. We have infinite, unlimited H2 gas. It doesn't come into play. Let's try some practice problems. Here we've got 3 practice problems to work with. Make sure your equation is balanced, and then use your mole ratio. I'm going to put about a minute on the clock, and then we're going to go over these. And remember, please pause if you need more time. When we look at the answers to these questions, we are going to get these results. Now, let's look at each one of these in turn. All right, first, I want black ink. We're going to go carbon plus O2 makes CO2. This is one of the rare equations that starts off balanced. And so then when it comes to asking my question, if I want 4 moles of carbon dioxide, how many moles of carbon am I going to need? Here, whichever way you look at the relationship, right here I went from a 1 to a 4, so I quadrupled. So here I should go from a 1 to a 4 and quadruple. Or, if you don't like looking top to bottom, you can look at the 2 tops and then look at the 2 bottoms. My numerators are the same, so my denominators should be the same. For the second one, when we balance this equation correctly, we get 1, 5, 3, 4. And the question wants to know, if I use 5 moles of C3H8, how many moles of O2 am I going to use? And so now here I can look either, again, top to bottom and look at that relationship, and it's the same relationship for the oxygen, or top to top and compare that to bottom to bottom. Looking numerator to denominator, right? Looking down, I go from a 1 to a 5, so that's multiplied by 5. So my 5 for the oxygen should be multiplied by 5 to give me 25. Alternatively, I have a 1 to 5 relationship up top in my numerators, so I should have a 5 to 25 relationship in my denominators on the bottom. For the third question, we get a little bit of vocab mixed in here. Reactant and product. Reactant means anything on the left side of the arrow, while product means anything on the right side of the arrow. And before we keep going with that, let's address this question in the chat. Where does the 3 and the 4 come from? The 3 and the 4 come from balancing this equation. like we did in the past. You start with the biggest thing and you put a 1 in front of it. That gives me 3 carbons and 8 hydrogens. So I'm going to need 3 CO2s and 4 H2Os to get 3 carbons and 8 hydrogens so that my equation is balanced. They don't come into play because the question doesn't ask you about CO2 and H2O, but you need to balance the equation correctly before you can answer the question. Now, coming back down here to our third problem, right? Reactant, everything on the left, product, everything on the right. When I balance this equation, I get 2, 2, 3. So then they're saying if I start with 2 moles of the reactant, which is exactly what they give us to start with, how many moles of each product will be produced? 2 and 3. That's just taking the exact balanced equation. But this one, part B, starting with 1 mole of the reactant, this is the first time we're seeing less, right? We're seeing it reduce, right? 2 over 1. This was cut in half, so these should also be cut in half to give us our 1 and 1.5. And when we were balancing equations, I said it was not okay to have decimals or fractional numbers. But when solving a problem, it is very much okay to have those things. Right? You'll never put 1.5 in the numerator, but in the denominator, anything goes. And so what comes next, right? What do we do after this? What's the next hardest thing to do? And that's to start throwing in mole calculations, right? Looking at what mass to mole, mole to mass is. And when we look at these, we're going to have a very similar setup. We're going to do exactly what we did before. We're going to make sure our equation is balanced. We're going to convert using our mole ratio. But then we're also going to have to do a mass calculation. So let's see that in play here. We're looking at our H2 plus O2 makes H2O formula. We're going to balance it the same way we did before. And now we're going to look at our question. If we react 3 moles of oxygen with unlimited hydrogen gas, how many grams of water will be produced? So here we have 3 moles of water. And we want to know how many grams of water, 3 moles of oxygen, how many grams of water will be produced. When we use to solve our mole ratio, right, when we look at these two fractions and we try to complete them, we're going to get 6 for this question mark here. Is that the answer to our question? Is our answer 6 grams of water? And the answer is no, it's not. These numbers, it's a mole ratio. 2 moles, 1 mole, 2 moles, 3 moles, 6 moles. These numerators and denominators are always moles. So we actually have 6 moles of water, not grams. And so we need to check the periodic table. We need to look for the mass of H and O, so we can calculate what 1 mole of water weighs. H2O is H plus O. So 1 plus 1 plus 16. For a total of 18 grams per mole. So if 1 mole weighs 18 grams, 6 moles weighs 6 times 18, or 108 grams. We are starting our equation, right? We're starting our problem exactly the same way, balancing. solving using the mole ratio, but then we have the additional step of bringing in the masses. The numbers that you use in your mole ratios are in moles. So you have to be careful when you're looking at these things so that you're actually correctly identifying what unit goes on each thing. Let's take a look at some practice problems for this. All three of these are going to use the same formula. And we already looked at this, so we already know how it should be balanced. And then I'll do you a favor and I'll pull these numbers off the periodic table for you so you don't have to flip back and forth. Now again, I'm going to put a minute, minute and a half on the clock here for you. And remember, you can pause if you need more time. When we look at the answers to these questions, I'm going to have to rewrite my ink, but we are going to look at answers that look like this. Now, let's put the ink back and address these here. Each one of these is going to look at C3H8, and so we're just going to pull the important stuff from the equation, right? C3H8, it's always going to be a 1 there. And then we're looking at a different thing each time, right? For the first one, we're looking at grams of CO2. And so we pull our important stuff here. Based on the question, 1 mole of C3H8, how many grams of CO2? So we're going to plug our numbers into our little mole ratio here, and when we solve this out, we're going to see 3 moles of carbon dioxide. But they want grams. The question asks for grams. And so we need to do a little calculation. So we're going to look at carbon and oxygen. CO2 is C and O, so 12 and 16 and 16. 44 grams is 1 mole of CO2. If I have 3 moles of CO2, I multiply this by 3 to get my 132. For the second question, we're looking at grams of water compared to C3H8. And so we're going to clear this out. Again, we're only going to keep the important stuff from the equation up top. So that's the 4 and the H2O. And our question this time says 5 moles of C3H8 will make how many grams of water? We're going to use our mole ratio first. 1 to 5 is 4 to 20 moles of water. When we want to put our answer in, we're not going to put 20 moles because it's not asking us for how many moles. We're going to look up top at the periodic table, and we're going to say H2O is H plus O, 1 plus 1 plus 16, for a total of 18 grams to equal 1 mole of water. We don't have 1 mole, we have 20 moles, and so we're going to multiply 18 by 20 to get our 360 grams as our answer. For the third question, we're back to looking at carbon dioxide, and so we're going to pull the important bits from our equation here. And they're asking us half a mole of C3H8 is going to give us how many grams of CO2. So we're going to plug in and we're going to solve for our mole ratio. Right, 1 to a half is 3 to 1.5 moles of carbon dioxide. And then using that same 44 that we had before, right, for CO2, 1.5 moles of CO2 is going to be 66 grams if 1 mole is 44. So we're still using our mole ratio, we're still getting these values of moles, but we're throwing in this extra little mass conversion. And when we look at the hardest thing we're going to look at today, our mass to mole conversion, we're doing the exact same steps, just in a different order. Here in mass to mole problems, they give you the mass to begin with, and they ask you for moles. And that means we're going to still do the same 3 things, but we're going to do our conversion before we do our mole ratio. Let's set that up so we can take a look together. 2 H2s and 1 O2 makes 2 H2Os. They're giving me 48 grams of oxygen to work with, but I can't put 48 down here. That is incorrect. I must put a number of moles down here. This 2, 1, and 2, those are all moles. So whatever numbers I put down here for X, Y, and Z, those must also be moles. So I need to take my 48 grams of oxygen and turn it into moles of oxygen. So I'm going to look at my periodic table. O2 is O and O, 16 and 16. 32 grams is 1 mole. If 32 grams is 1 mole, 48 grams is 1.5 moles of oxygen. And that can be plugged in because it's moles. When I look how many moles of water can I make, 1 to 1.5 is 2 to 3. Now, these numbers aren't always going to be so clean. When we move on and look at these practice problems, these two practice problems I have to close us out, we're going to see numbers that aren't quite so nice. These all worked out. All right, everything so far has worked out to pretty clean numbers. What if they don't? Here we've got two problems. And for our first problem, I'm going to give you the equation, and I'm going to balance it for you so you can focus on solving the problem. And also, to be nice, let me give you these numbers off the periodic table. Chlorine rounds to 35.5. Aluminum rounds to 27. Now I'm going to give you about a minute, minute and a half to try to solve these two problems out, and then we're going to go over them. For these two problems, let's switch ink colors so we can see our answers. We've got a little bit of work cut out for us. The first problem gives us 100 grams of chlorine gas, which means we've got 100 grams of Cl2. Cl2 is chlorine and chlorine, 35.5 and 35.5 for a total of 71 grams per mole. That means 100 grams is 1.4 moles of chlorine gas. Which means when I go to solve out this problem and I want to know how much salt I can make, my ratio, 1 to 1.4, becomes 2 to 2.8 moles of salt. For the second problem, they give us 300 grams of aluminum. Aluminum is just Al by itself, and so there's no need to add anything together. We're just going to look at 27 grams per mole. And so if we have 300 grams, that's 11.11 moles. How many moles of aluminum oxide can we make with that? Let's look at our ratio. 4 to 11.11 is 2 to half of that, right? This 4 became a 2, so it got cut in half. 11.11 should also get cut in half, giving us 5.55 moles of Al2O3. Right, the numbers are not always going to be clean, but we always have this mole ratio to look at. We can always set it up this way, and so we see the ratio as easily as possible. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.